So, in earthquakes, we actually see both waves, longitudinal and transverse. So, P waves are principal waves are the compression and dilations. What type of wave is this? Longitudinal. Yeah. And S waves are the traditional sine curves. That's where the ground's vibrating up and down. And whenever an earthquake happens, both of these waves are created. How do we know what the inside of the Earth is? How do we know what the core is like? If we look at, so we can put seismic detectors all around the world, and we have a particularly strong earthquake. We'll see that P waves end up not going through the liquid outer core. P waves end up being stopped by the liquid, so P waves don't go through the liquid, while S waves can go through both liquid and solids. So we've detected and had it around the world. We figured out where the epicenter of an earthquake was, and we had very sensitive seismic detectors. We can actually see that based on solid or liquid, how the S waves are deflected. We'll learn about that later, how waves are reflected when they pass through different mediums. But we were able to very accurately map out the inside of the Earth just by feeling the earthquakes and how they travel throughout the Earth. We can find the shadow region where no P waves is detected. And we can see where the S wave traveled and bent through the liquid. So P waves is the earthquake, and these are just compressions. And remember, even though when you saw the animation of these particles, they look like the entire particles are moving to the right. But if you actually sit there and stare at any particle, they're barely moving. So the wavelength of a longitudinal wave would be what? So just like a transverse wave is crest to crest or trough to trough. Compression is what we call the crest of a longitudinal. Trough is the rarefactions. So it'd be A and B. Is any two identical portions. Now let's talk about wave interference. What happens when two waves combine? Imagine you have a long string and you shake it up and down and you make a wave. You make that S wave, that sine or transverse wave down it. And someone else does the exact same thing on the other side. Well, when the waves combine, what are they going to do? They can, but the string can't be in two places at once. Somehow the waves are going to add each other. One thing that can happen is, yes, they can cancel each other out. Or another thing that can happen is they add together and become stronger. So wave interference occurs when two or more waves interact with each other because they occur in the same place at the same time. The displacement or amplitude is going to be just the sum of the two waves. You just add them together. Very simple. So constructive interference is when the crest of one wave overlaps with the crest of another. Their individual effects add together to produce a wave of an increased amplitude. So if you have the crest and the crest overlapping, it makes a bigger crest. The destructive interference is when the crest of one wave overlaps with the trough of another. The high part of the one wave simply fills in the low part of another. So their individual effects are reduced or even canceled out. An example of this is wave. We're going to do a lot of wave interference later. But whenever you have two waves next to each other, you can even in water you can see them cancel. Can you see like this little? Can you see this little region where it looks like the straight lines coming out? That's the destructive interference. That's where the water is canceled out and the wave doesn't move. And these regions are constructive interference, to where the heights are actually increased. The farther you get from a wave, normally the wave loses energy due to friction and stuff. But the constructive interference can make these get bigger as they go out, or at least not lose as much amplitude because they're canceling each other out, or summing together, I mean. Then we have something known as standing waves. If we tie a rope to a wall and shake the free end up and down, we produce a train of waves. We send a series of waves down the rope. Now, because a wall is rigid, the wall isn't going to move. And what's going to happen is, what happens when you throw a basketball down to the ground? It bounces back up. It reflects. Whenever a wave hits a rigid object, such as a floor, it's going to reflect backward and send a wave. It's going to bounce off the wall. And what that means is we're sending a wave down the string, hits the wall, and that wave comes back. So we have a wave moving forward, and we have a wave moving backward. And they're going to interfere with each other. If you time it just right, we can create something known as a standing wave. It's called a standing wave because it looks as if it's standing still. Let's see if I can find... I had a really good one. I should have saved that link for IPC. So if I can see it like comes. Alright, I definitely can't do it manual. Let's do it oscillating. So this isn't a standing wave. Let's see if I can get the standing wave. And let's turn off damping. And let's reduce. Almost. Hello? So this is almost a standing wave. You can see it gets, we do add some damping to it. So here, definitely not standing. We can see that if we're not exactly tuned, it's not that very big. But as soon as I get it to where they perfectly add together, you'll see the amplitude. This is not a good simulation. Let's see if I can find a better one. had like a really good program, but I do not know what I did with it. Come on, I know they were here. I'm watching my old videos. I don't think I recorded me using it for this class for third period. Oh well. Let me just look up standing waves.
So what we have here is a frequency generator. It's connected to what's called a wave driver. It's just a speaker. It's going to pump up and down at whatever frequency I set this guy to. When this guy pumps up and down, well, he sends a wave. Constructive or destructive interference at any one point. But if I set it here, for example.
So this is a standing wave. So the wave is coming down here, hitting this point and bouncing up, and right when it's bouncing up, another wave is coming over and colliding with it at the exact moment that we get constructive interference here, meaning the amplitude is going to increase, and we get deconstructive interference right here. And it looks as if the wave isn't moving.
I have what's called a standing wave. That is, the wave that's sent down and reflects constructively interferes with the next wave that comes down right at this point. Now the waves that reflect, that come down and reflect, destructively interfere with the incoming waves right here. And that's called a node. I can touch it and it still is working. So the node is not moving. Here it's moving up and down, and here it's moving up and down. And we'll see that in a second with the high-speed camera.
So that's what it looks like in slow motion. It is still a transverse wave.
So here we have what's called the second harmonic. It's the second possibility for a standing wave for a string that's held at both ends. Because notice, this is a node, this is a node, and the middle's a node. So we have three nodes for this wave.
So that's the second one. This is the first.
This number, so 8.5.
Watch as he transitions to it. It's more better than the other one. But
and there we go.
They're going to keep getting bigger, but they'll eventually friction will cancel it out so it doesn't infinitely get big. If there was no friction, it theoretically get big enough to break the string. So this is the first.
I can find any of the other harmonics. well, 3 times 8.5, I guess that was that.
So the second,
25.5.
and this will be the third.
And there we go. So that's the third harmonic. Well, it's 1/2 wavelengths. And it's easier to see speed. So check out this shot with the high-speed camera and verify for yourself that it is 1 1/2 wavelengths.
So you can see we have 1 wavelength right here, and then 1/2 a wavelength right there. Have y'all ever...
So again, third harmonic.
Have you ever had a cup of coffee, and while you're walking, it starts splashing out of your cup? Do you know why that is? So these harmonics depend on the length of the rope. If you have a cup of coffee, and depending on your walking speed, you can make, so depending on the diameter of the coffee mug, or any drinking glass, and your walking speed, so we have a circle, when you walk forward or when you jump up and down, you could have a wave come over here, hit the front side of the coffee mug, bounce backward, and if you match it so that the frequency of these waves matches the fundamental frequency of the resonance of the cup, these sloshing motion will get higher and higher and higher until it jumps out of the coffee mug. Only way to change that is either reduce the volume of the drink significantly or change the speed at which you're walking. Do you know how they break wine glasses? With your voice? It's also a standing wave. Breaking wine glass. Slow motion.
So this is a note.
Hey kids, are you in elementary school like us? Do you love science? Well, we love...
Shockwaves from a punch can do damage to the human body. Now we're going to... Jamie Vendera, motion camera, to see...
What's this?
That's it. This is the exact tone to make this...
So when you hear it and you hear things humming, it's because it reaches its fundamental frequency. It's the frequency that produces standing waves. It's the natural frequency that it likes to oscillate at, because standing waves so the circular, it's going to keep circling around and constructively interfering with itself.
particular glass vibrate. When the tone...
Let's see if
Alright,
this
I
is...
took 10,000 frames per second, and I took 1 second. If I were to play back this whole video, it would take 8 minutes to get through.
So, we can see the standing wave. This is now in 2 dimensions, though.
It felt like the whole goblet vibrating is actually the rim bending back and forth, 337 times a second, the same rate as the sound waves. If I draw in the sound waves, you can see what's happening.
So as soon as it gets to one
wave
side, it
comes
pushes
out of
it
the
at the
speaker
exact moment.
and pushes the side
So
of the wine glass.
it's adding a wave, constructively interfering. It's adding a new wave into the system at the exact moment to constructively interfere with the wave already in there. So the wave is going to get stronger and stronger and stronger as long as you match that frequency.
The glass bounces back just when another sound wave pushes it again. If the timing or frequency of the sound waves is exactly right, the motion will build until the glass breaks.
So that's a standing wave. So we have a incident wave, the wave going forward, and then we have the reflected wave coming back, and they constructively interfere. Nodes are the region of minimum or zero displacement. So one of the nodes, we consider it to be your hand. The wall is going to be another node, and then we have multiple nodes in. So in this bottom image, there's 3 nodes. Node at your hand, node in the middle, and node at the right. Some places don't include the endpoints as nodes. I do. The antinodes are the regions of maximum displacement and energy. They're the portions that move the most. If you shake the tube with so half a wavelength is the fundamental node, or the first order. A full wavelength is done by doubling the frequency. So any multiple of the fundamental is also a standing wave. Let me illustrate that. So let's say that you have a rope of length L, and let's say that the fundamental frequency is 10 hertz. You'll produce a standing wave. It'll hit this wall, and then it'll bounce off. And at the moment it bounces off, you send a downward down it so that you get constructive interference. If you double this frequency now to 20 hertz, you get this. First, going to hit the wall, bounce off, come back, and we get this. This is the second order. The fundamental is 10 hertz, so if I multiply it by 3 hertz, or 3, I mean, so 3 times 10 is 30, you get this. Where it'll bounce off, and again, any multiple of this fundamental, so this is half a wavelength. So half lambda. This would be 1 lambda, this would be 1.5 lambda, and this would be 2 lambda, twice the wavelength. Things like that. Trying to find another video. One cool experiment is taking a metal plate, putting a speaker under it, and putting sand on the top.
Did you want to create some cool physics art without having at different notes?
So, almost everything has a fundamental frequency. Well, not everything, but a lot of things do.
Change the frequency here. I'll sprinkle a little sand on the plate, and now watch this.
So the waves are coming in and hitting the edge of the edge and bouncing backward. The point right here is where the speaker is placed. So sound waves are vibrating through the material, hitting the edge and bouncing back. And we can see areas. What is this darker? Where do you think all the sand is moving to? The node or antinodes? So nodes are places without very much movement. Antinodes are the maximum displacement. Yes, because the nodes aren't moving very much. It's the antinodes that are vibrating up and down quite a bit, and so they're pushing them toward the nodes.
The sand moves on the plate into beautiful, though unusual patterns. As I find higher and higher special frequencies, the patterns on the plate get more intricate. How awesome is this? But it does kind of sound...
It's really weird whenever you do it on like a two-dimensional surface like that. This is actually what you're hearing on musical instruments. You tune the strings to fundamental frequencies. And so when you tap it, it's going to vibrate at some multiple, mostly the first order fundamental frequency of the string. You can, again, when you pluck something or make a sound on something, it's going to hum at whatever its fundamental or standing wave frequency is. And it doesn't matter if it's circular or if it's... I actually have a cooking pot at my house that is a perfect shape that anytime you bang it, it gets really, really loud hum. It's really well made in creating standing waves in it. Let me look at the test. I do not think my test... Did I break it up? Yeah, I broke it up. The Doppler effect is going to be on the next test. How much time do we have? Yeah, I have time. Alright, I'm going to go grab my standing wave generator.